In this module, we will consider wave motion. Waves are a traveling disturbance in some medium. For the disturbance to travel, the medium must tend to return to its undisturbed state. Adjacent parts of the medium must be coupled in some way so that a disturbance at a given location also causes a disturbance in its neighborhood. The wave travels with a speed of propagation, and this speed depends on the details of how adjacent parts of the medium are coupled. As a wave travels in some direction, the medium through which the wave is traveling may undergo different kinds of oscillations. Distinctly different kinds of oscillation represent different types of waves. Any wave is some combination of two basic types of waves. Transverse waves are those waves in which the medium oscillates in a direction perpendicular to the direction in which the wave is traveling. On the other hand, longitudinal waves are waves in which the medium oscillates in the direction parallel to the direction in which the waves are traveling. It is easiest to visualize transverse waves because the medium oscillates perpendicular to the direction in which the waves propagate. So let's consider a wave traveling down a long string held taut at both ends. At t equals 0, the string is pulled sideways, giving the wave an initial profile given by f of x. When we release the string, the displacement will start to travel as a wave in both directions down the string. If we are very careful in how we pluck the string, we can make the displacement travel in only one direction. Consider the wave profile f of x at t equals 0. The peak in this profile occurs at a position x we label as x0, which is around 5 in this figure. After a certain amount of time, the profile will shift to the right by a distance delta x, which is given by the amount of time which has passed t times the speed with which the wave is moving. Now, the peak in the profile f of x will be at the same argument to the function x0, but this x0 will be related to the position of the wave by the relationship that x0 is equal to x minus delta x, where delta x is the distance the wave has traveled, or x minus vt. This relationship is true for any point, not just the peak, and we find that we can describe the wave profile by f of x minus vt. We see then that if we replace the x dependence of the wave profile by x minus vt, we get a wave which is traveling to the right. That is, it is moving in the direction of increasing x. But if we replace the x dependence of the wave profile by x plus vt, we get a wave traveling to the left. That is, traveling in the direction of decreasing x. The function f of x describing the profile of the wave is often called the waveform. In principle, it can be any desired shape or functional form you like. In the original example, where we simply pulled the string sideways and released it, the initial waveform was evenly split into left and right moving waves. That is, 1/2 of f of x plus vt plus f of x minus vt. In order to get the wave to move only in one particular direction, we had to be very careful in how we created the initial profile. In the previous example, the waveform f of x was non-zero over only a very short span of x. This kind of waveform is very often called a wave packet. But for linear waves, it is more common to consider sinusoidal waves. Now, there are deep reasons for this connected to what's called Fourier theory, but we won't be delving into this. It's just important to know that sinusoidal waves are a very, very important form of waves to understand. A sinusoidal wave repeats itself over a distance of lambda called the wavelength of the sinusoidal wave. If the wave travels with a speed of v, the time capital T it takes the wave to return to its original pattern satisfies that the wavelength is equal to the speed times capital T. This time for the wave pattern to repeat is called the period of the sinusoidal wave. And in terms of the wavelength and period, we can rewrite the equation for a sinusoidal wave as a times sine of 2 pi times the quantity, x divided by lambda minus or plus t divided by the period, where the minus sign corresponds to a right-moving wave and the plus sign to a left-moving wave. As with simple harmonic motion, it is useful to define the frequency of the sinusoidal waves as being 1 over the period, and also the angular frequency omega as 2 pi over the period, or 2 pi times the frequency f. It is also useful to define for periodic waves an angular wave number k, which is related to the wavelength in the same way that angular frequency omega is related to the period. And in terms of these angular quantities, it becomes very simple to express a sinusoidal wave as a times the sine of kx minus or plus omega t, where again the minus sign corresponds to a right moving wave and the plus sign to a left moving wave. In summary, we see that the temporal aspects of a sinusoidal wave are characterized by the angular frequency or the period or the regular frequency, while the spatial aspects of the sinusoidal wave are characterized by the angular wave number or the wavelength, and the speed with which the waves propagate are related to these quantities in the following ways. The speed can be equal to the ratio of the wavelength to the period, or the product of the wavelength and the frequency, or the ratio of the angular frequency to the angular wave number. Notice that each point on a traveling sinusoidal wave behaves exactly like a simple harmonic oscillator. If we replace the sign in terms of cosine using a trigonometric identity and regroup it, we see that we can write the wave so that it looks just like a simple harmonic oscillator, where we have cosine of omega t plus a phase constant, but this phase constant now depends on the position and wave number of the particular wave. Let's remember that y represents the displacement away from equilibrium of some particular point in the medium as the wave travels through it. We can also take the time derivatives of this displacement, just like we did for a simple harmonic oscillator, and obtain equations for the speed and acceleration of that point as it moves away from equilibrium. It's important to keep in mind that the speed of the oscillation is not the same thing as the speed with which the wave is traveling. That is, v sub y is not the speed of propagation, v. Remember that for transverse waves, v sub y is moving perpendicular to the direction of v itself, and for longitudinal waves, while v sub y will be parallel to the direction of v, it will not be the speed of propagation. The description we have given for one-dimensional linear waves as behaving as some function of x plus or minus vt is true for all waveforms. And the description of these waves in terms of the wavelength, period, angular frequency, and angular wave number applies to linear sinusoidal waves traveling in any medium. But waves travel at some speed, and they also carry energy with them. And these quantities are intimately connected to the medium through which these waves travel. For waves traveling on a string, the speed of the waves can be expressed in terms of the tension of the string, T sub s, and the mass per unit length, mu sub s, of the string, and the speed is given by the square root of the ratio of the tension to the mass per unit length. Now, it's very important not to let yourself confuse the tension in the string with the period of the waves, because both of these tend to use the same letter, capital T, to represent them. This is why we put the subscript, sub s, on the tension in the string, so hopefully you won't get confused between these quantities. The other thing to keep in mind is that this formula for the speed of the wave on a string holds so long as the amplitude of the wave is small. If the amplitude becomes too large, then the tension will not be constant throughout the string. Because each point on a sinusoidal wave behaves like a simple harmonic oscillator, each bit of oscillating string of length delta x carries with it a little bit of energy. That energy, delta E, is given by the equation for the energy in a harmonic oscillator, 1/2 Ka squared, where K is the effective spring constant of the oscillator. But for sinusoidal waves, we need to write this in terms of the mass of the little bit of string which is moving and the angular frequency with which it is moving. So we wind up with 1/2 delta M, the little bit of mass, times omega squared times a squared. And we can write this little bit of mass in terms of the mass per unit length of the string times the length of that little bit of string. Now, while this is interesting, what we're really interested in is how much energy is being transported through the string. That is, how much power the oscillations carry. And power, of course, is given by the rate of change of the energy, and we can express this as 1/2 the mass per unit length of the string times omega squared times the amplitude squared times the speed of propagation of the wave. And notice that this equation is specific for a string since it involves the mass per unit length of the string, but similar formulas will hold for different mediums. But the details, of course, depend on what medium the wave is traveling through.